Hello, my calculus Padawans. Welcome to Chapter 3, Section 3.4, the Chain Rule Part 2. Before we get into more problems with the chain rule, I want to remind you of a couple properties of logarithms because, spoiler alert, we're going to talk about the derivative of the natural log function, but we'll get to that. Here are the basic four properties that you have to remember when dealing with logarithms. First, the natural log of 1 is equal to 0. Let me remind you of why that is. And that has to do, and it's easier if we go ahead and look at the graph of the function of natural log, which I'll draw over here on the side. So if I draw out the graph of the natural log, remember that that is going to look a little bit like this function right here. And we have a vertical asymptote. We have a vertical asymptote right here at x equals 0. And the graph of the natural log function passes through the point 1, 0. So when I take the natural log of 1, I naturally get 0 for my answer. The second rule, when you have the natural log of a product, you can turn that into a sum of the two individual natural logs. When you have a natural log of a number raised to a power, you can bring that power out front and turn it into a multiplication problem. When you have the natural log of a quotient, you can turn that into the difference of those two individual natural logs. For this problem, we're going to expand the logarithm. What that simply means is we're going to take this very condensed form of a natural log like we see here, and we're going to rewrite it out using those properties of logs from the previous screen. So what I want you to notice that you have a quotient here and you have something raised to a power. So we're going to use both of those things kind of expand out the logarithm. It's really kind of just a one-step process. So I'll use that 2 that's in front. I'll use that 2 that's in my exponent and write it as 2, and then it's 2 times the natural log of 2x minus 1. That deals with that first using the property with the exponents. And then the quotient. So that changes this from a quotient, a division problem, into a subtraction of that other log. So the natural log of the quantity 2x minus 1 squared over 4 turns into 2 times the natural log of 2x minus 1 minus the natural log of 4. Similar down here in number 2. I see the quotient, I see this radical. Remember that in fact means that that's raised to the 1/2 power. So when I expand it out, I get the natural log of 4x plus 1 minus 1/2 the natural log of x squared minus 1. I'm really hoping you guys remember this stuff from pre-calc. What's really kind of a cool trick with this problem, though, that I should mention, because it might come in handy later, I don't know, is that I can remember that this right here, x squared minus 1, remember that that's the difference of two perfect squares, the natural log of x plus 1 times x minus 1. And if I use and continue to use those properties of the properties of logarithms, I can rewrite that as the natural log of x plus 1 plus the natural log of x minus 1. Do you notice how I wrote that all in a big giant set of parentheses, right? Got the big parenthesis of that sum of the natural logs. That might come in handy, I don't know. Maybe. This brings me to my rules. The derivative of the natural log of function of x is equal to 1 over x. Now, we do have this stipulation. X has got to be greater than 0. Okay, x has to be greater than 0. And the second rule, the derivative of the natural log of u would be some function here, is equal to 1 over u times du dx. Or sometimes they write it as u prime over u, where u is greater than 0. I think of it like this. The derivative of the natural log of Bob. There's good old Bob. It's equal to 1 over Bob times dBob. So this is really like a chain rule problem, really. And we just have to make sure that Bob's greater than 0. Because remember, you can't take the natural log of a negative number anyways. So it would be a restriction on the domain of the problem. Let's take a look at 2 example problems that we have here. Y equals the natural log of 5x. Again, remember that that's 5 times x. So the derivative would be the natural log of Bob. So it's 1 over Bob times dBob. Or if we simplify that all down, right, we could have 5 over 5x, which is just 1 over x. Number 2, y is equal to the natural log of x to the third minus 1. Again, the derivative. 1 over Bob times d Bob. So my final answer would be 3x squared over x to the third minus 1. Not too bad. Of course, they will get a little more challenging. Like here in number 3, we have y equals x natural log of x. And you just have to recognize this as the product rule. Remember what I said last class. You have to recognize what it is that you see. So if I'm taking the derivative, I would do the first times the derivative of the second. So that's the derivative of the natural log of x, plus the second, the natural log of x, times the derivative of the first. When I simplify that all down, let's hear this is x times 1 over x. That's just 1. Plus natural log of x times 1 is the natural log of x. What about the other one? Y equals the quantity of the natural log of x to the fourth power. Or this is chain rule, Bob to the fourth. So the derivative of Bob to the fourth is 4 times Bob to the third power times d Bob. Don't forget about that d Bob. I'll finalize my answer as 4 natural log of x to the third over x. I haven't seen this notation used very much, but sometimes they use we write like cosine squared. I have seen them write this as the natural log cubed of x over x. Don't be too confused if you see that notation. I've seen it pop up, not really on the AP exam, but I have seen it in some college textbooks, kind of like the same way that you think of sine squared. This is natural log cubed of x. Means the same thing. Okay, so the natural log of the square root of x minus 1, and I want to find the derivative of that. It might be helpful. It might be helpful for you to think of this as the natural log of x minus 1 to the 1/2 power. Might be helpful. Hopefully you can see the chain rule going on here as well. It may be double chain rule, although the derivative of that most inside function we'll find out is just 1. So maybe we don't need to think of it that way. But anyways, the derivative of the natural log of x minus 1 to the 1/2 power. So this would be Bob, the natural log of Bob. So the derivative is 1 over Bob. So that's x minus 1 to the 1/2 power times d Bob. Okay, so the derivative of x minus 1 to the 1/2 power. That's 1/2 x minus 1 decrease that exponent by 1 to the negative 1/2 power. Or if I just write that out and simplify it down just a little bit more, I could make that 1 over the square root of x minus 1 times, let's see here, that would be 1, that 2 would be on the bottom. And that x minus 1 to the negative 1/2, well, that would be x minus the square root of x minus 1 on the bottom as well. And if I multiply that out together, let's see here, that's 1 over 2. The square root of x minus 1 times the square root of x minus 1, that's just x minus 1. That would be my final answer. It simplifies down fairly nicely here. Let me show you an alternative way to do this same problem. If I know that I can rewrite my function as the natural log of the quantity, x minus 1 to the 1/2 power, couldn't I apply my rules of logarithms and write that as 1/2 the natural log of x minus 1? And now when I take my derivative, f prime of x, I would get 1/2, that's the constant, times the derivative of the natural log of x minus 1. So that's 1 over Bob times d Bob, which is just 1. So I would end up with f prime of x being equal to 1 over 2 times the quantity of x minus 1, the same way I did the previous problem. So applying my rules of logarithms, that condensing and expanding properties, can make this problem a lot easier to do. As you'll see in this problem, oh my gosh, f of x is equal to the natural log of x times x to the third minus 1 to the fourth all over the square root of 2x squared plus 4. Can you imagine taking the derivative of this? I mean, that's chain function or chain rule with product rule with the chain rule and another product rule and another chain rule and a quotient rule in there. Oh my goodness, it's got like everything in it. Oh, I don't want to touch this one. Not with a 6-foot pole. So here we go. Here's what the real trick is with this. Natural log will allow us to expand this logarithm. So instead of me having to worry about all that stuff, what I can do is I can use my expanding properties and rewrite this as the natural log of x plus 4 natural log of x to the third minus 1 minus 1/2 the natural log of 2x squared plus 4. Now watch how easy it is to take the derivative of this. I just take the derivative of each part individually. So the derivative of the natural log of x is 1 over x, plus, that's 4. 4 times the natural log of Bob, so that's 1 over Bob times d Bob, minus 1/2, again, get the natural log of a different Bob. Okay, so that would be 1 over that Bob times d Bob. When I simplify this all down, what do I end up with? I end up with 1 over x, x, plus, that would be 12x squared over x to the third minus 1, minus, well, when I simplify this all down, that 1/2 times the 4x would just turn into 2x over 2x squared plus 4. That's really nice. That's not near as bad as what I thought the answer was going to be. Now, if you did take the derivative of it and tried to use the chain rule and the product rule and all that kind of stuff, you'd end up with an answer that looked very similar to this, but probably multiplied out a little differently. Unfortunately, sometimes things are difficult, a little more difficult. When I look at it in the form of this problem, f of x is equal to x squared minus 1 to the 4th over the square root of x plus 5, I don't have the natural log in front of it. Therefore, this is going to be a little bit more difficult to take the derivative of. So how do I handle this problem? I mean, if I did it the way that it's written, I'd have to use, let's see here, chain rule and quotient rule mixed together with another chain rule down there on the denominator. I just know I'm going to mess something up if I try to do it that way. Natural logs really made that previous problem a lot easier by me being able to expand that expression. Well, we can do that here too. So here's what I'm going to do. I'm going to rewrite this, and I'm going to add a natural log in front of that expression. Okay, but remember, I can't just add a natural log to that expression because I feel like it. So if I add this natural log over here on the right-hand side, I need to make sure I do it over there on the left-hand side too. All right, that allows me to look at the natural log of y is equal to, that now allows me to use my expanding and condensing properties of the logarithm to rewrite this as 4 natural log of x squared minus 1 minus 1/2 the natural log of x plus 5. And at least on the right-hand side, once I take the derivative of both sides, it's going to be a lot easier to do. A word about notation here. The symbol for taking the derivative is dx. This means I'm about to take the derivative of both sides. So let me just write that out here. So that tells me that in this step, I'm going to take the derivative of both sides. So if I take the derivative here of the right-hand side, I need to take that same derivative of the left side as well. This kind of helps me with some of the algebraic properties of calculus, like I have to keep the equations still very balanced here. Okay, let's just, we'll worry about the left-hand side in a minute. Let's go take the derivative here of the right side. So the derivative of 4 natural log x squared minus 1. Well, the 4 is the constant, so I have 4 times, that's the natural log of Bob, so 1 over Bob times d Bob, minus 1/2 times, I got the natural log of Bob, I got 1 over Bob times d Bob, which just happens to be 1. So again, I'm ignoring the left side, and I end up with 8x over x squared minus 1 minus 1 over 2 times the quantity of x plus 5. Which, if I work to get a common denominator over there on that side, if you trust me, I'm going to multiply the first fraction by x plus 5 over x plus 5, and a 2 as well, and the second one an x minus 1. And if you believe me, this whole thing simplifies down to give me 15x squared plus 80x plus 1 over 2x squared minus 1, x plus 5. Okay, so that actually simplifies down to give you that fraction right there. Let's talk about the left-hand side. The derivative of natural log of y. Okay, that's a little trickier. So this is me taking the derivative of the natural log of y. Well, we're not going to treat it any different. It's the natural log of Bob. So the derivative of the natural log of Bob is 1 over Bob times d Bob. Now, what's the derivative of y? That is dy dx, right? That's the symbol that we use for the derivative of y. You want to use a y prime, use a y prime. dy dx is better, though, here, and I'll show you why. when we get down here to the next step, we have 1 over y times dy dx equals that mess that we have over on the other side. Remember what we're trying to figure out. We were trying to figure out what dy dx was equal to. Dy dx is equal to this mess right here, plus 80x plus 1 over 2 times x squared minus 1 times x plus 5. But if you look here, we have this 1 over y factor that we have to deal with. So how do I get rid of this 1 over y factor? Well, I multiply both sides by y in order to make that 1 over y go away. Okay, well, what's y? Well, I don't want to reintroduce something new into the equation or keep a variable y. My original problem had x's in it. My final answer has to have nothing but x's in it. So what I will do is I will take this expression, this dy dx equals, and I know it's 15x squared plus 80x plus 1 over the 2, the x squared minus 1, and the x plus 5, and we have to multiply it by y. Well, what is y? Y is the original problem that we started with. So x squared minus 1 to the 4th over the square root of x plus 5. That would be a good enough final answer. I mean, maybe we want to simplify some things down a little bit, because if you notice, we got an x squared here and an x to the, so maybe we want to simplify some things down a little bit. So once I simplify that down, dy dx equals, okay, let's see here. That will give me an that'll give me an x squared minus 1 to the 3rd power times this 15x squared plus 80x plus 1 over, let's see here, I got 2, and I have x plus 5 to the 1/2 power. Wow. Trust me, folks, that is actually easier than trying to do it the other way. Even though it's a lot more involved, it's a lot easier than trying to do the quotient rule and the chain rule all wrapped up into one problem like we would have to do here with number 7. Okay. What if I had f of x equals the natural log of the absolute value of sine? Now, here, that absolute value in front of the sign is just to make us not take the natural log of negative values. So that's all that that's there for. It's just kind of to protect us so that we don't get any errors when we're trying to find the derivative here. We're not going to treat this any differently than we did any other problem. This is the natural log of Bob, and the derivative of the natural log of Bob is 1 over the sine of x, 1 over Bob times d Bob. So I end up with cosine of x over the sine of x, which simplifies down to be cotangent of x. That one's actually not that bad. There's a couple other rules that are worth looking at here. Okay, we have the derivative of our power function. So the derivative of a to the x is the natural log times a to the x. And that can be translated over here to the one that's over here on the right as the derivative of a to the Bob is equal to the natural log of a times a to the Bob times d Bob. Okay. If we have the derivative of a log with a base that is not e, right? This is not your natural log base. This is log with a base of a. So log base a of x, the derivative of log base a of x is equal to 1 over the natural log of a times x. Or if you think of it in terms of the derivative of the natural log of a of Bob is equal to 1 over the natural log of a times Bob times d Bob. In some instances, it actually might be easier if you view the natural log of natural log base a of x in terms of that change of base formula. I don't know if you remember that from pre-calc or not, but we can rewrite the natural log base a of x. Sorry, I said natural log. I meant log base a of x as the natural log of x over the natural log of a. And then when I'm writing out that expression, that's really 1 over the natural log of a times the natural log of x. And now maybe you can see why that 1 over natural log of a is in my final answer. Because if I take the derivative of that 1 over the natural log of a is my constant. Let's take a look at 2 problems that deal with those new rules we just came up with. So y equals 3 to the 4x, that's number 9. So if we're going to find the derivative of this, let's see here. Based upon what that said, it was the natural log of a. Okay, so a is 3 in this problem. So it's the natural log of 3 times 3 to the 4x, right? Just like the derivative of e to the x is e to the x, when we have that a to the x, we have an a to the x in the problem. It's just this natural log of a that we have out front. And then don't forget the dbob. Don't forget dbob. So the derivative of 4x, which is just 4. So my final answer, which probably would be better written as 4 natural log of 3 times 3 to the 4x. Looking at number 10, I have log base 4 of the sine of x. Again, I'm a big fan of using the change of base formula with this, especially since it looks a little more complicated. So the natural log of log base 4 of sine of x, I'll change to the natural log of sine x over the natural log of 4. So that would make me 1 over the natural log of 4 times the natural log of sine of x. If I take the derivative, that 1 over natural log of 4 is a constant. So I'm multiplying that by the derivative of the natural log of sine of x, which is natural log of bob. So 1 over bob times dbob, which there's my cosine of x over sine of x. So my final answer would be the cotangent of x. Oops, not cosine. Let me fix that. The cotangent of x over the natural log of 4. Folks, that wraps up the lesson today. So please, here's your homework assignment. It's the same thing that's posted up there for you in Canvas. Good luck with the problems, and I'll see you next time.